Hi folks, welcome to what I think is the most important lesson of this course, where we finally find the slope of a tangent to a curve. So we're going to have a few definitions to start with. Number one, we're going to think about what a secant is. So a secant is a line that touches a curve in two places. So there would be an example of a secant. It touches here and here. And secants give the average rate of change over an interval. A tangent is a line that just touches the curve at a single point. So if I drew the tangent to this function right here, it would have the same steepness as the curve at that point, or it would represent how steep it is at that point. And tangents give the instantaneous rate of change at a point, or in an instant. This all has to do with slope, so we might as well refresh our memories on what slope is all about. Slope is sometimes just called rise over run. That means the change in y over the change in x. And change is always final minus initial, so sometimes you'll see it written this way. Y sub 2 minus y sub 1, x sub 2 minus x sub 1, or x2 minus x1. To put this in context a little bit, we're going to think about an opening problem. Suppose you decide to throw a pumpkin off an 80-meter tall building. You know the distance fallen in meters by the pumpkin after t seconds is given by d equals 5t squared. That's really, roughly, how it would work on planet Earth. And so the pumpkin's going to hit the ground after 4 seconds, because if you put 4 in for t, you get 80 meters. And we're going to do three things. We're going to graph the distance fallen for the first 4 seconds for this pumpkin. We're going to find the average speed over the first 4 seconds, and then we're going to find the speed of the pumpkin as it hits the ground, which is right at time equals 4 seconds. So let's think about this graph. I actually had the computer produce the graph. Here it is. It's a parabola, not surprisingly. Right at 4 seconds, it's fallen 80 meters. So actually the rest of this graph doesn't make any sense. It's not like the pumpkin drills down into the earth faster and faster. But you can notice that the distance fallen, say, in the first second is like 5 meters. The distance fallen in the second is more. It's 15 meters. And so on. This disparity changes, and that's because the pumpkin is picking up speed. So if we wanted to do part B here, if we wanted to find the average speed over first 4 seconds. First 4 seconds, or until it hits the ground. Well, I mean, you could just look at the graph and say, okay, average speed is going to be 80 meters, and that takes 4 seconds. So 20 meters per second. Okay, if it goes 80 meters in 4 seconds, on average it goes 20 meters per second. And we could also think about that graphically, though. That's actually equivalent to the secant slope right here, okay, between the point 480 and 0, 0, where it starts. So the slope of that secant, which we already said secant is going to be average rate of change, would be, let's label these, x1, y1, x2, y2. So it would be y2 minus y1 all over x2 minus x1. Let's give it some meaning with some units, meters per second. Again, 80 meters in 4 seconds, or 20 meters per second. Now the next thing we are asked to do is find its instantaneous speed. Right at 4 seconds, how fast is it going? Well, we've already established that the slope here is going to give us speed, because slope is delta y over delta x, and y is measured in meters, x is in seconds, so that's going to be a speed or a velocity. If we want the instantaneous speed, that's the job of the tangent slope. Okay, so I could just draw in the tangent and try and find its slope. But obviously I'm freehanding it. Like, it's not going to be absolutely perfect. So you might say, okay, well, I know what to do. Let's find the tangent slope. We'll just use Since a tangent only has one point, let's just use these numbers twice. Okay, so it'll be y2 minus, I'm going to call the y1 the same thing, all over x2 minus x1 meters per second. Oh my, that gives us 0 over 0 meters per second, which is not 0, it's undefined. And we've seen some of this 0 over 0 shenanigans before. It kind of led us to limits. So, oh dear. We can't use the same point twice. That's the fundamental problem of finding a tangent slope. On the other hand, if you use 2 points, then you're looking at a secant. So what can we do here? Well, I guess if we want to approximate the tangent slope, maybe we could use points that are really close together. Like if I just used those two, I'd probably get a good approximation of the tangent slope. Not perfect. So what I did on the next slide is I just showed some points that we could get that are close to 480. So once again, we've got this point here of 480. That's the one where it actually hits the ground. And just before it, there's a point 3.9, 76.05. Just take my word for it. If you sub in 3.9 into this, you'll get 76.05. Okay. And so the slope of this tangent, using these 2 points, is going to be, it's got a rise of 3.95, and it's got a run of 0.1. So this is going to be slope meters per second. We'll get 39.5 meters per second, which is steeper than the 20 meters per second we got over here. And that makes sense. You can see that the tangent is steeper than that green secant. Okay, but what could you do after that? I guess you could use points that are even closer together. You could use this one right here, 3.99 and 79.605. Okay. And what's going to happen there? Well, you can take my word for it, but if we use those 2 points, we're going to get a slope that's 39.995 meters per second. If you want to, you can try that on your own. What if we use points that are closer still? Well, if we used this one right here and 480, you're going to get a slope in that case that is 39.99995 meters per second. I mean, what do you think the slope really is? What do you think that speed is? Looks like it's closing in on 40. Okay. You could even use a point that's beyond it, even though the pumpkin will have hit the ground. You could still use the model. And if we used these 2 points, you get a slope that's a little more than 40, 40.005 meters per second. So my guess for the tangent slope at x equals 4, or t equals 4, I guess, my guess is that it's going to be 40 meters per second. So here's the rub, though. We're still finding secant slopes. We're using 2 points. And they're really close together, so they're excellent estimates. But you could always go a little closer than you already have. So we could have the point 3.9999999 until the cows come home and whatever its y value is. That'll give us a better estimate. We're going to do something that is a little bit abstract to try and get around this idea of 2 points that are close together. Let's look at general points, and maybe we'll take it outside the domain of just this pumpkin that's going to hit the ground. But say you had the point 480. So there's 4, there's 80. Okay, and we cared about its tangent slope there. You could also pick another point that's just a little bit over. Let's call that distance between them h. And h stands for horizontal distance, so that the x is going to be 4 plus h. And then the y is just going to be whatever the function is at 4 plus h. Okay? And for us, I think our function, let's get it out of those d's and t's, our function was basically just this. That's going to give you the secant slope between 480 and any point. If we generalize a little bit further, And this will give us something that we can practice with in a moment. What if it wasn't 480? What if you had a point that you cared about? Let's call it A. And it's going to have a y value that is just f of A. Let's call this function f of x. So here's a point, A, f of A. And then another one that's just a little bit over. Let's call that distance h, so that this point right here is going to be a plus h, f of a plus h, right? Because the f of something just gives you the y value. We could use those two to figure out what the secant is, the secant slope between them. Okay. Secant slope, m secant, is just going to be y2 minus y1 all over x2 minus x1. So the secant between these two is going to be, let's label these, x1, y1, x2, y2. General points here. F of a plus h, that's the second y value, minus f of a, that's the first x value, x2 minus x1. Or in other words, the slope of the secant between any 2 points is given by this. That's still just rise over run. Okay, this is rise, difference in y's, and the run is just, you can see it right there. It's that h. Okay. Right now, that's still just a secant slope. Let's generalize a little bit more, or let's sort of codify what we've got. So the average rate of change over some interval is equivalent to the slope of the secant. The slope of the secant that joins points A, f of a. So A is a point that we care about. And A plus h, a point that's just a little bit over. And f of a plus h is given by, we'll go through this process again. That's x1, y1, x2, y2. So the slope of the secant will be y2 minus y1 all over x2 minus x1. Yeah, on the bottom it even kind of says, aha. Okay, or f of a plus h minus f of a all over h. Okay, that is the slope between any 2 points, or the secant slope. Now, what do we want to happen? We want those points to be as close together as they could ever be. We want this h to be as little as possible. But it can't be 0. And if it's 0, then you have the same point twice, so you can't actually find slope. And that's where limits come in. To turn a secant slope into a tangent slope, all we need to do is use a limit. So the instantaneous rate of change at some value is equivalent to the slope of the tangent. If we want the slope of a tangent, add x equals a, and we'll get better notation later. Here's all we do. We say it's the same as the secant slope, but those 2 points need to be as close together as possible. H needs to be infinitely close to 0, or infinitesimally small. And that's really all there is to finding a tangent slope, is plugging in this little formula that is essentially grade 10 rise over run. It's important enough that I'm going to put it right here again. This is the big deal here. The slope of the tangent at x equals a is f of a plus h minus f of a over h, and we take the limit as h goes to 0. Okay, so we make the points infinitely close together, or the gap between them infinitesimally small. Let's put it to use on a question. So let's imagine that we've got this function over here, 2x squared minus x. I'm just going to factor this so that I can help myself graph it. That means that it's a parabola with x-intercepts at 0 and a half. And it looks something like this. And it goes up here. And it goes up forever and ever, right? If we want to find the average rate of change on this, that's not really calculus-y stuff. average rate of change is equivalent to secant slope. So to do that, all we need is 2 points. Okay? We need the point 1 something and the point 3 something. This right here, this means a domain, right? It means the domain from 1 to 3. And that interval notation, you'll see it more and more. So if we want to find that secant slope, well, I just need to find the corresponding y's that go with each of those x's. So f of 1 would be 2, 1 squared minus 1. Oh, so that's 2 minus 1. So the point 1, 1 is on this graph. If I find f of 3, well, that will be 2 times 3 squared minus 3. And so what will that be? 18 minus 3 is 15. Okay, and now we can just go ahead and try and find the secant slope. It's just going to be, here's x1, y1, x2, y2. So y2 minus y1 all over x2 minus x1. So sorry, I don't know if I said that right the first time. y2 minus y1 all over x2 minus x1, 14 over 2. Or the average rate of change is 7. Okay, or the slope of the secant. Now, if I want to find the instantaneous rate of change, or the tangent slope right at x equals 3, that is probably going to be steeper. And we've got this handy-dandy formula now. Slope of the tangent at x equals a is the lim as h goes to 0 of f of a plus h minus f of a all over h. For us, this 3 here, that's our, quote, a value. That's the value that we care about. Okay, so we want the tangent, not just anywhere, but the tangent at x equals 3. At x equals 3. So that's going to be lim as h goes to 0 of f of 3 plus h minus f of 3 all over h. And what I think you should do is go off to the side and figure out what f of 3 plus h and what f of 3 are. Okay. So we actually already found f of 3. F of 3 is 2 times 3 squared minus 3, or 15. F of 3 plus h, I'm going to pick a different color here. F of 3 plus h. Now think about that. If we said f of 1, you'd put 1 in for x. If we said f of 5, you'd put 5 in for x. If we said f of pi, you'd put pi in for x. If we say f of 3 plus h, you just put in 3 plus h for x. Okay? And you put it in each time it appears. And put it in brackets. So let's try and clean that up a little bit. Minus brackets 3 plus h. And this is the annoying part where we've got to just do a bunch of algebra here. I've got to FOIL this out, so I'll get 9 plus 6h plus h squared minus 3 minus h, or 18 plus 12h plus 2h squared minus 3 minus h, no, minus 3 again, minus h. Okay, so that's 15 plus 11h plus 12h squared. That's all stuff that I found so that I can sub it in to this limit. So I went off to the side. The slope of the tangent at x equals 3 is just going to be the limit as h goes to 0 of, let's get that color roughly back, of the f of 3 plus h, that's 15 plus 11h plus 2h squared, minus f of 3, which was 15. I'm going to put it in brackets just to be careful here. And I can see those 15s they're going to add to 0. So the slope of the tangent at x equals 3 is the lim as h goes to 0 of 11h plus 2h squared all over h. I really think that you should factor this before trying to simplify it. Okay, because true cancellation happens from factored form. So I factor the top, I take an h out, and that's where I can actually divide these. Just plugging and chugging with some algebra. And eventually I'm getting rid of most of my problems. Okay, as h goes to 0 of 11 plus 2h, now we can finally sub in. So the slope of the tangent at x equals 3 is going to be 11 plus 2 times 0, or just 11. There's that tangent slope. Okay, was it kind of a pain? I mean, yeah, we had to worry about doing all this extra stuff off to the side just so that we could plug it in. But in the end, it was just a fairly simple limit to deal with. Finding the average rate of change, that did not require any limits at all because average rate of change is just secant slope, which we could do probably since grade 10. Let's do another one. G of x is 1 over x plus 2. So when I can graph them, I kind of like to. That's just your basic butterfly graph. Move to the left, or basic hyperbola. And it looks like this. So we're wondering, what is going to be the secant slope between 1 and 3? Okay. And maybe I'll take up a little less space doing the secant slope this time. If I put in 1 for x, I'd get 1 over 1 plus 2. So that would be 1/3. If I put in 3 for x, I get 1 over 3 plus 2. So I'd get 1/5. You can see that the slope's going to be negative, but I mean, it's going to be fairly gentle slope, like a small negative number. Okay, and that gives me my x1 and my x2, x1, y1, x2, y2. I can find that tangent slope just by going y2 minus y1 all over x2 minus x1, or 1/5 minus 1/3 all over 2. Now here I'd like to use my nifty little nested fraction trick, which is to find the lowest common denominator of all those little fractions and see what happens. So when I multiply that through, I'm going to keep going here. I'll get 5s will divide out, so I'll have 3 minus 3s will divide out 5 all over 2 times 3 times 5. That's 30. So negative 2 over 30, or negative 1/15. And that gives us our secant slope. And like we expected, it's negative, pretty gentle. I think if we go ahead and find our tangent slope, which is what it's going to ask us here, tangent slope at x equals 3, that's going to be still negative, but even closer to horizontal. It's just barely going downwards. So if we want the slope of the tangent at x equals 3, that's going to be the lim as h goes to 0 of f of 3 plus h minus f of 3 all over h. Okay, that's just using this formula right here that is at the heart of finding all tangent slopes. I would be inclined to go off and, first of all, maybe use the letter g for all of these, because we're talking about the function g in this case. I'd go off to the side, and I'm going to find g of 3 plus h, and I'm also going to find g of 3. So g of 3 would be 1 over 3 plus 2. We actually already found it. That's 1/5. G of 3 plus h would be 1 over 3 plus h plus 2, or 1 over 5 plus h. So now I have the stuff that I can plug in. You can do that as part of this step, but I think it's tough to do that along with, figuring out what to write here. So it's g of 3 plus h, which is 1 over 5 plus h, minus g of 3, which is 1 over 5. That's the stuff that I found over here. Just like with numbers, you've got an issue here with nested fractions. So let's deal with them. Okay, I'm going to times the top and the bottom by 5 plus h. This is not the only way you can deal with these nested fractions, but I think it's pretty slick. And so that'll give us the slope of the tangent at x equals 3 is the limit as h goes to 0 of, we'll get 1 times 5 here, minus 1, not 5, but 1 times 5 plus h. And this will all be over. On the bottom, you'd have 5h by 5 plus h. And it's a limit, so we just kind of work it through. Lim as h goes to 0. So 5 minus h all over 5h by 5 plus h. We still keep the limit notation because we haven't subbed in yet. Maybe you can tell on top that those 5s are going to add to 0. So the slope of the tan at x equals 3, and again, there's better notation coming, is going to be negative h all over 5h by 5 plus h. And now, finally, some cancellation can happen in division. These divide out. And that gets rid of your problem. That means that you can probably finally sub in. Lim as h goes to 0, negative 1, 5 by 5 plus h. You might be saying, well, there's still an h on the bottom. Yeah, but it's not the kind that causes us a problem. Let's just try and sub in 0 and see what happens. Okay, it'll give us negative 1 times 5 plus 0. Well, yeah, that isn't a problem. Or negative 1 over 25, okay, which is still a negative slope, like we expected. It is a more gentle negative slope than that secant one was, because that seemed like reasonable. It was evening out or sort of straightening out. So that's all there is to finding tangent slopes, is using this formula. At this point, you could head to the textbook, page 92 and 93, and do 1, 9, 10, and 11, A only for each of those. I'm going to keep going and do maybe one more without a graph on here, but you could tap out here if you like. So in this one, it would be a pain to graph it. Hopefully we've got the idea here, though, that what we need for an average rate of change is 2 points. We need 2 something and 5 something, because these are x values, right? This is an interval. And I got to find the corresponding y. So h at 2 is going to be whatever it works out to be. Great, there's one value. I'm going to get rid of this stuff and do the same for 5. H at 5 is going to give me the corresponding y value there. 5 squared minus 3 times 5 plus 1. Okay, so that would be 50 minus 15 plus 1, so 36. So the slope of the secant is just going to be y2 minus y1 over x2 minus x1. So y2 minus y1 all over x2 minus x1. 33 over 3, or 11. No limits needed. If I want to find the slope of the tangent at x equals 5, so we have to infer here that it's the tangent slope, but it says at a number, not over an interval. So the slope of the tangent at x equals 5 is going to be the lim as h goes to 0. Now it's annoying here, this says h of x. Let's change it. Let's change it to f of x. That'll be f of 5 plus h minus f of 5 all over h. And I have to go off to the side and figure out what f of 5 is. We've actually already done that. We found it right here. It's 36. And I have to figure out what f of 5 plus h is. And this is where the algebra becomes tedious. So that would be 2 times 5 plus h all squared minus 3 times bracket 5 plus h plus 1. Okay. So we're going to have to hop in here and carefully FOIL this out. 10h plus h squared minus 15 minus 3h plus 1. Or 50 plus 20h plus 2h squared minus 15 minus 3h plus 1. Let's put some terms together. We'll get 36 plus 17h plus 2h squared. Yeesh. That was a fair bit of work. But the rest of it after here becomes plug and chug. So f of 5 plus h is 36 plus 17h plus 2h squared. F of 5 is 36. You can see those 36's add to 0. So we get 17h plus 2h squared all over h. And we keep going. I'm going to factor it so that I can safely evaluate this limit. Now I've got h's that divide out. And really, at this point, my problem's gone. Lim as h goes to 0 is going to be 17 plus 2h. And now I can sub in. So that's 17 plus 2 times 0, or 17. That is the slope of the tangent at x equals 5. So again, you can do some practice from the book. If you want some more questions to do, you could check out these ones here. Find the slope of the following secants and tangents. And here are the alleged solutions. Hopefully I didn't make a goof. All right, so congratulations. You can now find a tangent slope, which is really half of what calculus is about. I hope the video has been helpful. Good luck with the material, folks, and take care.